Welcome back to Chemistry Matters, Unit 6, the mole and stoichiometry. In our last video on the Unit 6 playlist, we executed 2 conversion problems and had our students use dimensional analysis. You'll be using this technique a lot as you perform chemical calculations. I mentioned the mole early in the last video, and you heard our teacher reference it near the end of the last segment. So now's a good time to investigate the concept of the mole. What exactly is a mole in chemistry, and why is it such an important concept? The mole is a number, an incredibly large number. It's equal to 6.02 times 10 to the 23rd power. Just as a dozen represents 12 of something, a mole represents 6.02 times 10 to the 23rd of something. For example, if a bottle contains 1 mole of helium gas, you know that it contains 6.02 times 10 to the 23rd helium atoms. What if a bottle contained 0.5 moles of helium? How many helium atoms would be in the bottle? It would contain half a mole, which is 3.01 times 10 to the 23rd atoms. It works exactly like a dozen or a half dozen. So again, the question you might be asking yourself is, why is this important? Well, when dealing with masses of macroscopic substances, objects we can easily see, we typically use units such as grams or kilograms. These units work just fine if we're massing out rocks or dumbbells or just about anything else we can easily weigh. However, if what we're concerned with massing is a hydrogen atom, these units become more cumbersome. Measuring the mass of one hydrogen atom is very difficult, but if we gather together a large number of hydrogen atoms, it becomes much simpler to measure the mass. For example, the mass of a typical hydrogen atom is around 1.66 times 10 to the negative 24 grams. Who wants to be going around doing calculations with numbers that are so ridiculously small? Here's where the mole can become really helpful in chemistry. Measuring the mass of a mole of hydrogen is much easier since a mole is such a huge number. Scientists began using the mole as a unit of measurement back in the 1800s, and they found it to be so useful, the decision was made to name the number of atoms in a mole, 6.02 times 10 to the 23rd, Avogadro's number, in honor of Amedeo Avogadro, a very influential Italian chemist of the 19th century. Avogadro's number became one of the base units of measurement in the SI system in 1971. With that in mind, let's use the mole to count atoms. We'll take a step-by-step approach to learn how it is possible to relate number of atoms, mass, and volume, all by using the concept of the mole. As we learn these steps, keep your eyes open for this graphic organizer, which will appear on screen when we start mole calculations. This graphic organizer will help you organize your thoughts and remember the goal of each problem. This organizer shows the types of calculations we're likely to perform, such as how many atoms are in a mole, what is the mass of a mole of atoms, or what is the volume of a mole of atoms, for example. Now let's go back to our classroom, where our students are learning how to use moles to count the number of atoms in a chemical sample.
The mole is the SI unit that measures the amount of matter a substance has and is often abbreviated as MOL in problems and calculations. The mole can be related to the number of particles in a substance or its mass in grams, or it can also be related to the volume of a substance. A mole is simply 6.02 times 10 to the 23rd representative particles. This is another example of an equivalent statement, like we talked about before. 1 mole equals 6.02 times 10 to the 23rd. Representative particles could be atoms, molecules, or formula units. We can convert from moles of a particular substance to representative particles using Avogadro's number. Or we can convert from particles to moles. You just have to know what type of particle you're starting with and what you're having to convert to. You'll get a better understanding of what I mean if we solve a problem together. The first problem is, how many molecules of water are there in 0.360 moles of water? So does this look like a conversion problem?
Yeah, the question gives us moles, and it wants molecules as an answer.
Excellent. So how could we use dimensional analysis to solve this problem?
Well, we have 0.360 moles to start with, so that needs to go into the upper left-hand corner of the conversion chart.
Yes, that's the correct first step. What's next?
Let's see. We need to let the notes guide the conversion, so we need to write the unit moles of water in the lower right.
Exactly. Now, we want this next column to be a conversion factor, right? And remember, conversion factors are just equivalent statements written in fraction form.
We need to convert to molecules, and we have moles. Is there an equivalent statement for those?
A mole is just 6.02 times 10 to the 23rd of something, so I guess that would work for molecules also, right?
Yeah, and molecules, atoms, and formula units are all examples of representative particles we described a minute ago.
That's right. And Avogadro's number over 1 mole would be the correct conversion factor to use for this problem. So let's make sure the units cancel out and that the unit we're solving for is in the upper right-hand corner of the conversion chart.
They do cancel. We have moles of water in the numerator in one step and in the denominator of another. So they cancel, and we're left with molecules of water in the upper right. So all we need to do is multiply everything in the numerator, 0.360 times 6.02 times 10 to the 23rd molecules over 1. So 2.17 times 10 to the 23rd molecules of water are found in 0.360 moles of water.
Great job. Let's try one more conversion problem involving representative particles and moles. This one asks, how many moles of magnesium are there in 1.25 times 10 to the 23rd magnesium atoms? Who wants to get us started on this one?
I'll try. We need to identify what we're given and what we're trying to solve for. Then place what we're given in the upper left-hand corner of a conversion chart. It looks like we're given atoms this time, and the question wants us to convert that to moles. So let's put 1.25 times 10 to the 23rd magnesium atoms in the upper left-hand corner of a conversion chart.
And of course, we have to let the units guide the conversion. So our next step is to write the units in the lower right-hand box, and this time they're magnesium atoms.
And this is the part where we have to turn an equivalent statement into a conversion factor. But I'm not quite sure where to go from here.
Well, I think it's helpful to constantly remind yourself over the course of these problems what it is you're trying to solve for. It will help you if you can reason through it.
Oh, yeah. Well, since we need to convert to moles and we have particles, well, atoms, to begin with, we can use the equivalent statement 1 mole of magnesium equals 6.02 times 10 to the 23rd magnesium atoms. This time, we'll need to put Avogadro's number in the denominator, and we can put 1 mole of magnesium in the numerator.
That's it. Then we can cancel the units of magnesium atoms, and since we have the unit we're trying to solve for, which was moles of magnesium, we just need to do the math, which in this problem is going to be 1.25 times 10 to the 23rd times 1 mole of magnesium. Then divide that by 6.02 times 10 to the 23rd.
We then divide the numerator by the denominator.
And we get 0.208 moles of magnesium.
Great job, everyone. It seems like you have a good grasp on converting from moles to representative particles and vice versa.
Our students just got a great introduction to converting between moles and particles. Notice on your graphic organizer that our students were converting from moles to representative particles, and from representative particles back to moles. If you'd like more help with this concept, you can check out our closer look video on converting moles to particles. If you're ready to continue, now we can make the concept of the mole even more useful by connecting the mole to the mass of substances in grams. To do that, though, it will help to get a little more information on how atomic mass is measured. The unit we use when dealing with masses of atoms is called the AMU, and it stands for atomic mass unit. The AMU is based upon the carbon-12 atom, and the creators of the AMU decided that one atomic mass unit equals 1/12 the mass of a carbon atom. You can think of it this way. A typical carbon atom has a mass of 12 AMU. Now take a look at the periodic table where carbon is. You'll notice carbon has 12.011 listed as its atomic mass. If you had a chance to watch the closer look videos from Unit 3, you got to see how these masses are calculated. Practically speaking, the idea that we would ever measure the masses of a small number of atoms is not realistic. So wouldn't it be nice to have a way to tie all of these concepts together in a way that gives us units that are easy to work with, yet at the same time gives us an accurate description of the numbers of each type of atom present? This is where the mole, the number 6.02 times 10 to the 23rd, comes into play. It's essentially a proportionality constant that allows us to create a conversion factor to convert from AMU to grams, or vice versa if we should choose to do so. Scientists have used dimensional analysis to show that the mass of a single carbon atom is 1.99 times 10 to the negative 23rd grams. Again, this is not a very practical measurement because we would never deal with a single atom. But what would be the mass of carbon if we happen to have a mole of carbon atoms? If we multiplied 1.99 times 10 to the negative 23rd grams by Avogadro's number, also known as the mole, which is 6.02 times 10 to the 23rd, we get 11.98 grams of carbon. Does that number for carbon look familiar? Look at your periodic table and the average atomic mass of carbon. The average atomic mass of carbon is 12.01, very close to 11.98. And when we account for all the isotopes of carbon, we find that 1 mole of carbon atoms has a mass of 12.01 grams. Look to the left at boron with an atomic mass of 10.81. So 1 mole of boron atoms has a mass of 10.81 grams. And look at nitrogen on the right. It has an atomic mass of 14.01. So 1 mole of nitrogen has a molar mass of 14.01 grams. The atomic mass of each element also represents the mass of that element in grams if we were to have a mole of atoms of that element. This is known as the molar mass. Molar mass is the mass in grams of a mole of a substance. Molar mass is the same number as the average atomic mass for an element. So to summarize, if we have a mole of atoms of any element, then we would know what the mass would be in grams. We know this by looking up that element's mass on the periodic table. So there are really 2 important pieces of information that we can derive from those masses listed for each element on the periodic table. 1. The average mass of a single atom of that type of element in atomic mass units. And 2. The mass in grams of a mole of that particular element, or in other words, the element's molar mass. That's why the mole concept is so important to chemists. It connects the submicroscopic world with the world that we can see. It allows chemists to count atoms by weighing, and ultimately it allows us to calculate the mass of reactants that are needed for a particular reaction, or the mass of products that would be made from a reaction given a specific amount of reactants. And that's exactly what stoichiometry is, the calculation of the quantities of reactants and products involved in a chemical reaction. But before we jump into calculations involving stoichiometry, let's head back to our classroom where our students are doing some more conversions using dimensional analysis, this time using the mole and the measurement of mass.
Earlier, we explored how to find the mass in grams of a mole of atoms of any element simply by looking at the masses listed on the periodic table. Well, we can do the same thing with compounds. By simply summing up the molar masses of all the elements that are found in a compound, we can determine the molar masses. Before we get started with some problems involving molar masses, I wanted to get your hands on some moles, literally. So what I have here in this box are several samples of substances that are exactly 1 mole. For example, this is a mole of aluminum. Okay, notice it has its mass written there on the outside of the beaker. So what does it say?
26.98 grams.
Right, very good. So 1 mole of aluminum atoms has a mass of 26.98 grams. Here's the next one. 1 mole of zinc.
That one's mass is 65.38 grams.
Good, good. So next up, we have a mole of calcium.
Well, that's not what I thought calcium would look like. I mean, I thought it would be in big chunks, you know, like bone or something.
Yes, sometimes calcium does look more of what you're describing, but as we've learned, all elements can take different forms. All right, back to the question. What's its mass?
40.08 grams.
Good, good. And I've got one more. This is a mole of iron. What does its mass say?
A mole of iron has a mass of 55.85 grams. Did you weigh all that out?
Yes, I did. And you know what's amazing? I know roughly how many atoms there are in each one of these containers. You know what's even more amazing? It's the same number.
Wait, what?
I know. There are molar masses of all these elements written on the beaker.
So each one has 1 mole, or 6.02 times 10 to the 23rd atoms of the element inside.
Hold on. These all have the same number of atoms? How could their masses be so different, but they have the same number of atoms?
That's a great question. Does anyone know the answer?
Well, they may all have the same number of atoms, but the individual atoms have different masses.
Right, so an iron atom would be more massive than an aluminum atom, right?
That's exactly right, and that's what makes the molar masses different, even though they contain the same number of atoms. Now, I have a few more samples in here. This is 1 mole of water. What is its mass?
18.02 grams. And did you just get that number by adding the mass of 1 oxygen to the mass of 2 hydrogens from the periodic table and then round off for the significant figures?
That's exactly right. So 1 mole of water has a mass of 18.02 grams. So because there's 1 mole of water in the bottle, I can tell you that there are 6.02 times 10 to the 23rd molecules of water floating around in here.
Whoa, what else do you have in that box?
Okay, here's a mole of sodium chloride, which is common table salt.
The mass is 58.45 grams. So is there a mole of sodium chloride molecules in there?
Well, remember from Unit 4 that covalent compounds form molecules while ionic compounds form formula units. Sodium chloride is an ionic compound, so technically we say that there's a mole of formula units of sodium chloride. But you have the right idea. There are Avogadro's number, or 6.02 times 10 to the 23rd units of sodium chloride in that container. Now that we've been able to see and hold moles of various substances, let's see if we can use dimensional analysis to work a few problems involving molar mass. Remember, the molar mass of a substance is the mass in grams of a mole of a substance. This first question asks, how many grams are in 9.45 moles of dinitrogen trioxide, or N2O3? Robbie, do you want to get us started on this one?
Sure.
Great.
We need to determine what we're given and what we need to find first. So we're given 9.45 moles of dinitrogen trioxide, which is N2O3. So we'll need to set up a conversion chart and put that in the upper left-hand box.
Good. And what do we always do next?
Let the units guide the conversion. So we bring the moles of dinitrogen trioxide down to the box on the bottom right.
Okay, so we're going to need a conversion factor for the next step, right?
Yeah. Since we're solving for mass in grams, we should use the molar mass for the compound, kind of like what we were just looking at with the samples.
Very good. And what's the molar mass of dinitrogen trioxide?
We have to add up the masses from all the elements in the compound. So let's see. The periodic table tells us that the mass of nitrogen is 14.01. N2O3 has 2 nitrogens, so that's 14.01 times 2, or 28.02.
The periodic table also tells us that the mass of oxygen is 15.999, which we can round to 16.00. Since N2O3 has 3 oxygen atoms, we multiply the mass, 16.00, by the number of oxygen atoms, 3. So that is 16.00 times 3, or 48. So we add the mass contributed by nitrogen, 28.02, to the mass contributed by oxygen, 48. So the molar mass of N2O3 is 76.02 grams.
So our equivalent statement is 1 mole dinitrogen trioxide is equal to 76.02 grams of dinitrogen trioxide, and we can use that as our conversion factor.
Yeah, so we just need to put 1 mole of dinitrogen trioxide in the denominator and 76.02 grams in the numerator.
Then we can cancel out the units of mole N2O3.
And we're left with grams of N2O3. Then we need to multiply everything in the numerator. That's 9.45 times 76.02. Then we divide that by the product of everything in the denominator, which is just 1.
Okay, let's read the question again. How many grams are there in 9.45 moles of N2O3?
Our answer is 9.45 times 76.02, or 718 grams of N2O3, which is reported in 3 significant figures.
Very well done. Okay, let's try one more. Only this time we'll go from grams to moles. This question asks, how many moles are in 92.2 grams of iron 3 oxide, or Fe2O3? So, how can we work this one out?
Since we are given 92.2 grams of iron 3 oxide, let's put that in the upper left-hand corner. Then let's put the grams of iron 3 oxide in the denominator on the next column.
Okay, that sounds good. What would be next?
Well, next I want to convert from grams to moles. So I will put the molar mass of iron 3 oxide in the denominator, which is 159.69 grams. Then I'll just write 1 mole of iron 3 oxide in the numerator. That's the conversion factor that we need.
Exactly right. How did you come up with that number for the molar mass?
Looking at the formula, there are 2 irons and 3 oxygens. So I just multiplied iron's molar mass, 55.845 by 2, which is 111.69. Then I added 48, which I got from 3 times 16, which is oxygen's mass.
And I noticed you didn't round the molar mass of iron, and that was a good decision because iron's molar mass isn't extremely close to a whole number like oxygen's is. So it looks like you're almost done. How do you finish this calculation?
We can cancel units of grams of iron 3 oxide. Then we're left with moles of iron 3 oxide in the upper right-hand corner. And since that's what we're converting to, we're done, except for the math.
So we need to multiply 92.2 times 1, since those are the values in the numerator. Then divide by 159.69, and you get 0.577 moles of iron 3 oxide. So 0.577 moles of iron 3 oxide are found in 92.2 grams of iron 3 oxide.
Well done. Hopefully that wasn't too challenging.
Yeah, it really helps to follow the dimensional analysis steps.
Yes, you'll definitely want to keep the dimensional analysis steps handy as you get more comfortable working with problems that involve conversions. Does anyone want to quickly summarize those steps for us?
Identify what's given in the problem. Also figure out what you need to solve for.
Right. Then place what's given to you, the number and the unit, in the upper left-hand corner of a conversion chart.
Choose a conversion factor that'll get you to the next unit, making sure that the unit from the upper left also appears in the lower right.
And then let the units guide the conversion by lining up conversion factors so that the units cancel. And you can cancel the units as you go.
Right. And after canceling the units, multiply all the numbers in the numerator together, as well as all the numbers in the denominator. And then divide the numerator by the denominator.
And finally, check the units and your answer.
Great job, guys, and great summary, too. I think you're ready to put your knowledge of the mole and dimensional analysis to use as we learn how to use stoichiometry to solve problems involving real-life chemical reactions. I've prepared some supplies that will allow you to actually measure moles of atoms yourself. This is a way to connect all those calculations we've done to chemicals in the real world. Each team will try an example. Michelle and Sierra, I want you to try the example using table salt. And Robbie and Amaria, you'll try the example using water molecules.
Okay. It says measure out 1.25 moles of table salt, sodium chloride, in a clear, dry cup.
Okay, we have some salt right here. All right, so let's figure out how much salt we're gonna need. We can start by writing out 1.25 moles of sodium chloride. By writing 1.25 moles of sodium chloride into our conversion chart. Bring that unit of moles of sodium chloride into the denominator. So let's do that now. Then we'll have 1 mole of sodium chloride in the denominator. We'll need the molar mass in the numerator, and we'll know how to calculate the molar mass.
Let's check the periodic table to find the mass of sodium and chlorine.
Okay, the mass of sodium is 23, and the mass of chlorine is 35.45.
And there's only 1 sodium and 1 chlorine in sodium chloride, so all we have to do is add 23 to 35.45.
And that's easy. It's 58.45, which is the molar mass of sodium chloride in grams.
Right, so 1 mole of sodium chloride weighs 58.45 grams, so we can put that in the numerator of our conversion chart, then cancel out the unit of moles. So we multiply 58.45 grams times 1.25, and that should be our answer.
And that's 73.06. So 1.25 moles of sodium chloride is 73.06 grams.
Great, and we can start weighing the salt.
All right, well, let's put our goggles on first.
Okay, I'll put the cup onto the balance and zero it first.
A little bit more, maybe. All right, I think we're gonna need a little bit more. Let's try with the scoopula.
I think that's just about it.
Yeah.
Can we check our answers with you now?
Well done. Your calculations and measurements for 1.25 moles of sodium chloride is well within 2%. It's very accurate. Good job, guys.
Okay, so we need to put 4.52 times 10 to the 24th molecules of water in a beaker. In our conversion chart, we can start with 4.52 times 10 to the 24th molecules of water. Then we can bring down the units of molecules of water as the denominator in the next column.
Yeah, so then we can use Avogadro's number to convert the particles to moles. So let's put 6.02 times 10 to the 23rd in the denominator. And then we'll put 1 mole in the numerator. And that will be the equivalent statement.
Okay, that sounds good, but we need grams, right? We're really converting from particles to moles to grams. So let's make another box and bring down our units of moles.
Yep, that's right, because now we can use the molar mass of water to convert to grams.
Okay, so to calculate molar mass, we find the mass of hydrogen on the periodic table. It says that hydrogen is 1.008, so we'll need to double that for 2 hydrogens.
And the mass of oxygen is 15.999, but we only need 1 of those.
Okay, so when you add those together, you get 18.015 grams, the molar mass of water. We'll round that to 18.02.
So then we could put 18.02 grams of water in the numerator and put 1 mole in the denominator. So then we multiply everything in the numerator and do the same thing for the denominator.
Okay, so we divide that by everything in the denominator, and we get 134.6. So 4.5 times 10 to the 24th molecule of water has a mass of 134.6 grams.
Great, let's put on our goggles and get to work.
Okay, so we should place an empty beaker on the balance and zero it before we start adding any water. That way we'll have the best chance of getting accurate results.
Good idea. Let's pour the water in first, and then we'll use the pipette to finish it off to get the most accurate results.
Okay. I think we're good. Let's check with the teacher.
Okay. I think we're ready.
All right, let me check your calculations. Wow, great math, guys, and measurement too. Now let me ask you one question. Did you guys remember to zero the balance before you put the beaker on and measured the water?
Yes, because if we didn't do that, the measurement would have been artificially low because the beaker's mass would have been included in the measurement.
Excellent lab work. That is a common mistake in the lab, but you guys have done really well to avoid it. Good job.
Our students are using measurement to confirm their calculations of molar mass. And now's a good time for you to get some practice with that as well. Remember that the graphic organizer we showed you is a good tool for organizing your thoughts and planning your calculations, whether calculating grams per mole, moles per gram, or atoms in a mole. The same problems our students just did, as well as several others, can be found in the Chemistry Matters Toolkit. So we'll take a break here to let you get started on those. When you think you've got accurate measurements, check your answers with your teacher. By the way, if you think you want some additional instruction, we've provided some closer look videos that can help you with converting moles to number of atoms, as well as molar mass calculations. When you're ready to continue, I'll be ready as well at the top of the next video on the Unit 6 playlist.